In scattering, we will discuss three more topics: singlet and triplet state cross sections, scattering length, and effective range theory. And the first one is singlet and triplet state cross sections. When neutrons collide with protons, that means when you have collision, the protons and neutron spins, as we know, each have the value is half, can combine to get a total spin S equals Sp plus Sn. This can have magnitude either 0 or 1. That means if they are parallel or anti-parallel. If they are parallel, the spin is 1, and if they are anti-parallel, the spin is 0. So this can have magnitude either 0 or 1. The S is equal to 1 combination has 3 orientations. This is also known to us the spatial arrangement of spins. You will consider the z-axis as the direction, and it has 3 orientations corresponding to z components plus 1, 0 and minus 1. And the S is equal to 0 combination has only a single orientation. So for that reason, the S is equal to 1 combination is called a triplet state. That means it has 3 orientations. And S is equal to 0 combination is called a singlet state because it has only 1 orientation. Of the 4 possible relative spin orientations, 3 are associated with the triplet state and 1 with the singlet state. So we have 4 possible orientations. Only 1 is with the singlet state and 3 with the triplet state. And what you can assume, there is a possibility to arise any of these 4. That means each of these orientations or each of these orientations has a possibility to occur. That means 25% occurrence. That means 1 by 4. So 3 is from triplet state, 1 from singlet state. So for singlet state, 1 by 4 probability, and for triplet state, 1 by 4 plus 1 by 4 plus 1 by 4, that is 3 by 4. So as the incident nucleon approaches the target, the probability of being in a triplet state is 3/4, that means 3 by 4, and the probability of being in a single state is only 1/4, that is 1 by 4. If the scattering cross section is different for singlet and triple states, then you can write the sigma as 3 by 4 sigma t plus 1 by 4 sigma s. So this is an assumption that we are making. The cross section is different for singlet and a triplet state, and this is based on our last class experience, where we have shown that the triplet state cross section is not matching with our experimental values. So we have to correct it, and there we have used the concept that there may be a spin dependence. And here sigma t and sigma s are the cross sections for scattering in the triplet and singlet states respectively. And we have already calculated the value triplet state. It is 4.6 barns. And using the measured value of sigma equal to 20.4 barn. So 20.4 barn is a non-quantity, but using that triplet state we are getting it as 4.6. So for the low energy cross section, we deduce sigma s equal to 67.8 b. So actually in this equation you will substitute sigma t and sigma. And based on the calculations, you can get the value of sigma S as, it is a very large value. Actually, you are getting it as 67.81. And this calculation indicates that there is an enormous difference between the cross sections in singlet and triplet states. That is, the nuclear force must be spin dependent. We can verify our conclusions about the singlet and triplet cross sections in a variety of ways. One method is to scatter very low energy neutrons from hydrogen molecules. So, that means about the singlet and triplet state. Molecular hydrogen has two forms known as orthohydrogen and parahydrogen. In orthohydrogen, the two proton spins are parallel. This is orthohydrogen, and actually this small line represents the covalent bond between the hydrogen atoms. So spins are in the same direction, that means they are parallel. It is known as orthohydrogen, and while in parahydrogen they are antiparallel. Here you can see it. The difference between the neutron scattering, the difference between the neutron scattering cross sections of orthohydrogen and parahydrogen is evidence of spin dependent part of the nucleon-nucleon force. Actually, this is the cross sections per atoms, and this is the energy. You can see that this is the line for liquid orthohydrogen, and this is for parahydrogen. So you can see that there is a difference in the low energy scattering range. So this figure is just to mention that, or just to indicate that there is a difference in cross section for ortho and parahydrogen. That means the cross section depends on the spin. In the first case, that is S is equal to 0 state. S is equal to 1 state for orthohydrogen and S is equal to 0 for parahydrogen. So it is evident from this figure. So now we will define the second term, that is scattering length. The concept of scattering length was introduced by Fermi and Marshall. And for low energy scattering, we can define the cross section as sigma, limit sigma where k tends to 0 is given as 4 pi a square. This k tends to 0 is it defines, or it mentions a low energy scattering, and you are assuming that the scattering area may be a circular one or a spherical, so not only it's a spherical one. That is why you are writing the equation as 4 pi a square, and this a is called the scattering length. This a is called the scattering length, and we have sigma equals, already you have the equation 4 pi by k square sine squared delta. So you can have a comparison here, and when this k tends to 0, you can write this as delta 0 and this as say sigma 0. So or comparison, you can see that you have in place of this a square sine square delta by k square. That means a square is sine square delta by k square, or a will be square root of sine square delta by k square, and which can be either plus sine delta by k or minus. That means you have plus or minus limit k tends to 0 sine delta 0 by k, and the choice of sign is arbitrary. We can choose either plus sign or minus sign, but it is conventional to choose the minus sign. That is a convention that we have used. And even though the scattering length has the dimension of length, it is a parameter that represents the strength of the scattering and not its range, which means that scattering length means it is a distance up to which scattering is happening. That not at all. Actually, that A has a dimension of length, and it is a quantity related to scattering. That is why we are calling it as a term known as scattering length. And from the expression for A, delta 0 must approach 0 at low energy. That means as k tends to 0 in order to maintain scattering length a finite value. That means when we have delta 0 is small, you are writing it as delta 0 by k. So when this as k tends to 0, actually a number by 0 is infinity. But if both numbers are very small, you can say that it is not infinity. That is a way. That means this should also very small, which means that delta 0 must be also small. And when delta 0 is small, that means when sine theta, when theta is small, you can write sine theta as theta. That means you are writing it as delta 0 by k. That means we have the original expression A as minus sine delta 0 by k. You can now write as minus delta 0 by k. Or delta 0 as minus ak. Now, for low energy neutrons, we have this is the nuclear radial wave function that we have written as UR, which is C sine kr plus delta 0. And now you can write it as C sine kr. In place of this delta 0, it is minus ak. So it is C sine k as common factor r minus a. And when k is small, sine k of r minus a you can write as k into r minus a. That is u of r is ck r minus a. So this is an equation of straight line intersecting r axis at r is equal to a. That means you can have this is of the form y equals mx plus c, equation for straight line. And in y you have ur, and this is ckr represents mx. So this r is the x axis and this a represents the intercept c. So the intercept is obtained by extrapolating the radial wave function of u of r from the point just beyond the range of the nuclear force. And this is the custom that we are using. At the just beyond the range or at the range that you are taking as capital R. So at R is equal to capital R, you will draw actually we know that this is a equation, sine equation. So at a point where that sine curve meets the point small r is equal to capital R, you will draw a line. That means which is just, or it is you will be extrapolating, or from that line where that extrapolated line meets the r-axis, that point you are calling as the scattering length. And this is the figure from our crane. So actually this is the wave function in one case that you are calling as the bound state, and this is for the unbound state. You can see that this is the range small r is equal to capital R. So within that range, actually the sine has a peak value and then it decreases here. And here you can see that in the unbound stage, the curve goes on, and here only you are getting the peak. So we are taking only the required portion here. So you can see that this is the first one. That means the A1. That means the line is here. So here you are drawing the tangent at this point. R is equal to R. That means that line is meeting at the point R equal to say plus A, because this is R is equal to 0 point. R is equal to 0 point from where you are increasing the R value. So R is equal to plus A. And for this is the case of you are normally taking as repulsion, and we will explain these terms attraction and repulsion later. So in the second case, that means here, so this is the magnified figure. So this is the form. So from here, you can draw the tangent to only this direction, because you can't draw it here. This is the normal way of drawing tangent at this point. So at small r is equal to capital R, and it is meeting at a point. This is small r is equal to 0, and this may be at equal to small r is equal to minus n at the negative side. So this scattering length you can call as the negative scattering length, and this as the positive scattering length. And now we are saying that this positive scattering length corresponds to attraction and a negative scattering length corresponds to a repulsion. And we have drawn the two wave functions in a single figure. So this is the first case, A case, and this is the second one. So you can see that here the tangent meets A greater than 0, and here the tangent meets A from here, A less than 0. And this is for the unbound state, and this is for bound state, or this is scattering length is positive, this is scattering length is negative. The significance of positive and negative scattering length is that it tells us whether the system has a bound state or unbound, or unbound state. A positive scattering length indicates a bound state, and a negative scattering length indicates a virtual or unbound state. Now, the scattering length for singlet and triplet states. The total scattering cross section is given by sigma is equal to 3 by 4 sigma t plus 1 by 4 sigma s. This we have already written. And introducing AT and AS as the scattering lengths for the triplet and singlet states. Sigma t you can write as 4 pi AT square and sigma s as 4 pi AS square. Substituting, sigma is 3 by 4 4 pi AT square plus 1 by 4 4 pi AS square, or you are getting as sigma is 3 pi AT square plus pi AS square. And from this equation, experimental estimates of total cross section at 0 energy, this we have already mentioned, it is 20.4 bar. But the above equation is not sufficient to determine the values of AT and AS. To do this, another equation containing AT and AS, both in the form of measurements made at low energy, is needed. Because we have done this at low energy. This is provided by the coherent scattering experiment. It's an experiment that we will not discuss here, but the term coherent scattering is one in which amplitudes instead of intensities added up. That is the definition of this coherent scattering experiment. And now we are interested only that not on that experimental part, but on the data that we are getting from it. And coherent scattering experiments not only verify the spin dependence of NP scattering, but also enable to establish the signs of singlet and triplet states. The theory of neutron scattering from ortho and parahydrogen gives, we have this equation we are getting, the scattering cross section for parahydrogen is 5.7, 380 plus A square, and that of ortho is sigma para plus 12.9 AT minus A square. So you have two equations, and solving these you can get as 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 minus 23.55 and AT as plus 5.35. So the scattering length for the singlet state is negative and that for triplet state is positive. The negative scattering length of singlet NP scattering implies that there is no bound singlet state of neutron. And for scattering, you can see that when a proton is approaching, a neutron is approaching a proton, there can be attractive force or repulsive force based on this. But after that, it is scattering. Either it is attractive or repulsive, the neutron will scatter. But when they are bound together, like your neutron, there you can see that if it is a singlet state, the force between them will be definitely negative, which means that they can't be bound together. And if it is a triplet state, then they can be bound. So that is why we are saying that the negative scattering length of single NP scattering implies that there is no bound singlet state for neutron. And based on this, we have a theory now known as effective range theory, or which is also known as shape independent approximation. In this, the scattering cross-section for various values of incident neutron energies is expressed in terms of scattering length and a new parameter known as effective range. Therefore, the theory is known as effective range theory. The total cross-section for scattering you are writing as, actually you have this equation k cot delta 0, that is equal to 1 by a plus 1 by 2 r0 k square plus etc. This is an equation that we have assumed. We are starting from an equation assumption. And terms in higher powers of kr you are neglecting. So you will be taking only these two. And the quantity A is the zero energy scattering length. And the quantity R0 is our new quantity known as the effective range. Therefore, the total cross-section for scattering you can now write as sigma 0 is 4 pi by k square sine square delta 0. This is a non-equation. In that, this sine square delta 0 can be written as 1 by cosecant square delta 0, or it is 1 by 4 pi by k square 1 by, and cosecant square delta 0 can be written as 1 plus cot square delta 0. So that is 4 pi by, in the place of this 1 plus cot square delta, you are expanding it like k square plus k square cot square delta 0, and that can be written as sigma 0 is k square 4 pi by k square plus 1 by a plus 1 by 2 r0 k square. So you have an expression for total cross section for low energy scattering in terms of R0 and A. That means R0 is your effective range and A is your zero energy scattering. Like the scattering lengths, the effective range is different for singlet and triplet states. The advantage of this representation is that A and R0 characterize the nuclear potential independent of its shape, and hence the second name shape independent approximation. Actually, you are only considering about that wave function and not based on the potential that we are taking. We would repeat all the calculations done in this section, or we can do with a potential other than the square wave, like Gaussian potential, Yukawa potential, Gaussian, whatever may be. And we would deduce identical values of A and R0 from analyzing the experimental cross sections. We are getting the same values. The disadvantage is that we can learn little about the shape of the nuclear potential. If you are using A and R0, you will not be able to know what is the nature of your potential. That you can do only with other methods. And now we have assumed that, or we have deduced all the expressions based on the concept that our potential is a square wave potential. And that's all in this class. Thank you.